Hello and welcome. Have you ever wondered how chemistry really works? Like on the most basic level? Well, it all boils down to electrons. Today, we're going to learn how to write the address for every single electron in an atom, and all it takes is three simple, super powerful rules. All right, let's jump right in. So here's the game plan. We'll start by figuring out what an electron's address even is. Then, we'll go through the three key rules that tell us how electrons fill up that space. And to finish, we'll put it all together and actually build an atom, carbon to be exact, step by step.
Okay, so first things first. Before we can start placing electrons anywhere, we need to get the lay of the land. We need to understand the geography of an atom from an electron's point of view. Where do they actually live?
To make this really easy, let's use an analogy. Just imagine an atom is a giant apartment building. Now, if you wanted to find someone in that building, that's our electron. You'd need to know what floor they're on, which apartment, and finally, which room. That's pretty much exactly how an atom is structured.
So, the main floors of our atomic building, those are called shells. They're the big primary energy levels where you'll find the electrons. And just like a building, the farther you get from the ground floor, or the nucleus, the higher the shell number and the more energy the electron has.
Now, each floor, or shell, isn't just one big open space. It's divided into different apartments, which we call subshells. We give these apartments letter names, S, P, D, and F. On any given floor, the S apartment is the lowest energy, and it gets higher as you go to P, D, and then F.
And finally, inside each apartment, we have the rooms. These are called orbitals. An orbital is the specific spot where you have the highest chance of finding an electron. And here's the most important part. Each room, or orbital, can hold 2 electrons max. That's it, no more.
And check out how this all comes together. An S subshell is just a one-room studio, so it holds 2 electrons. A P subshell has 3 rooms, so it can hold 6 electrons total. A D has 5 rooms for 10 electrons, and an F has a whopping 7 rooms for 14 electrons. You see the pattern, right? The number of electrons is always just double the number of orbitals. Simple.
Okay, so we know the layout of the atom building. Now, how do we start filling it with our electron residence? Well, that brings us to our very first rule.
So, the Aufbau principle, it's German for building up, and honestly, it's just common sense. It says that electrons are lazy. They're always going to take the easiest spot available, which means they fill the lowest energy orbitals first. You fill the ground floor before you move up to the second floor. Makes sense, right?
And this diagram right here, this is your cheat sheet, your roadmap to getting it right every time. You just follow the arrows. You start at the very bottom, 1s. Then the next arrow takes you to 2s. Then you loop around to 2p. Then 3s. Loop around again to 3p. Then 4s. See that? It's a little weird. 4s actually comes before 3d. This map makes sure you never mess up the order.
So we're filling orbitals from the lowest energy up. Great. But what happens inside each one of those orbitals, those little rooms? That's where rule number 2 comes into play.
The Pauli exclusion principle is basically our 2 per room rule. We already said an orbital can hold a max of 2 electrons. But here's the catch. Those 2 electrons have to have opposite spins. Think of it like a north and south pole. We show this by drawing one arrow pointing up and one pointing down. This is to make sure no 2 electrons in an atom are perfectly identical.
All right, we've got one last major rule to cover. This one handles a very specific situation. What do you do when you have a bunch of orbitals that all have the exact same energy, like those 3 p orbitals sitting side by side?
Hund's rule is my favorite because it's just so relatable. I call it the bus seat rule. Think about it. When you get on a mostly empty bus, you don't sit right next to a stranger if there's an empty 2-seater available, right? You take your own seat first. Electrons do the exact same thing. To keep their distance, they'll each take an empty orbital in a subshell before they even think about pairing up.
Okay, enough theory. We've got the map, we've got the rules. It's time to put this stuff into practice. Let's actually build the electron configuration for a super important atom, carbon.
So if you look at a periodic table, carbon's atomic number is 6. In a neutral atom, that means it has 6 protons and 6 electrons. So our mission, should we choose to accept it, is to find the perfect home for all 6 of carbon's electrons.
The process here is really straightforward. We're going to start at the very beginning of our energy roadmap. We'll add our 6 electrons one at a time, and we'll apply our 3 rules, Aufbau, Pauli, and Hund, every single step of the way. Let's do it.
So this is our destination, the final orbital diagram for carbon. But how do we get there? Let's start with a blank slate. We've got our 1s, our 2s, and our 3 2p orbitals all empty and ready to go. Now let's place those 6 electrons.
Okay, electron number 1. Where does it go? The Aufbau principle says it goes to the lowest energy spot, so boom, into the 1s orbital. Now for electron number 2. It joins the first one in the 1s, but with an opposite spin. That's the Pauli exclusion principle. And just like that, the 1s orbital is totally full.
Next up, electrons 3 and 4. Well, according to Aufbau, we have to move up to the next lowest energy level, which is the 2s orbital. So electron 3 goes in. Electron 4 pairs up with it, but with an opposite spin, just like Pauli's rule says. Now the 2s is full. We've placed 4 electrons, 2 to go.
And now for the last 2 electrons. This is where Hund's rule, the bus seat rule, comes in to save the day. Instead of piling into the first 2p orbital, electron 5 takes one empty orbital, and electron 6 takes a different empty orbital. They spread out first. That's Hund's rule in action, perfectly illustrated.
And there it is. That's the final configuration written out. The 1s squared just means the s orbital on the first energy level has 2 electrons. The 2s squared means the s orbital on the second level has 2. And 2p squared means the p subshell on the second level has 2 electrons in it. That's the whole address.
Okay, that's great. We followed the rules, we wrote down some letters and numbers, but so what? Why does any of this actually matter? What does this address really tell us about carbon?
This right here is the big payoff. The electrons in the outermost shell, for carbon that's the 4 electrons in the 2s and 2p orbitals, have a special name. They're called valence electrons. And these are the only electrons that matter for chemistry. They're the social ones that interact and form bonds. Carbon has 4 of them, and that's why it can form 4 strong bonds, which is literally the backbone of all life on Earth. So this isn't just a nerdy exercise, it's the fundamental secret language of all chemistry. So the next time you look at a periodic table, remember these 3 rules. Because with them, you now hold the key. You have the power to figure out the electron configuration for almost any element. And once you have that, you can start to predict how it will act, who it will bond with, and what it will become. The entire world of chemistry is now open to you.